Hi, everyone. So, in the previous lecture from Monday, I introduced to you the semantics of our formal language. I also introduced to you how to construct truth tables for arbitrary sentences of our formal language. In this lecture, I'm going to provide the precise the precise definitions of the semantic notions, for instance, validity, entailment, equivalence, and these semantic notions, which came up intuitively earlier in the class, will now finally be given precise definitions within our formal logic. And the main upshot of that is that we will be able to use the method of creating truth tables to test whether sentences have these semantic properties or not. So in the first part of this lecture, I will give you the precise definitions of validity as well as other important semantic notions, which have already come up at an intuitive level. But again, now we're going to be able to give precise definitions of them. And then after doing that, I'm going to work through some practice questions. And these are actually questions from the problem set. So I'm going to work through some questions to show how to apply the method of truth tables from the previous lecture to determining whether certain sentences have these semantic properties or not. So we begin with the definition of validity. So last lecture, I introduced the idea of evaluation. An evaluation is an assignment of truth values to the atomic sentences of the language, as well as how those truth values percolate up given the meaning of the connectives. So with the idea of evaluation in mind, we can define validity as follows. An argument is valid just in case every valuation that makes each of the premises true, it's also a valuation that makes the conclusion true. So again, what this is saying is that a valid argument is one where every way of making all the premises true also makes the conclusion true. Or another way of putting that is that whenever the premises are true, the conclusion is as well. So again, on any assignment of truth values to the atomic sentences of an argument, whenever that assignment makes each of the premises true, we see that also the conclusion is true. And that's what it means for an argument to be valid. Now, a very closely related notion to that of validity is that of entailment. And you can think of validity and entailment as essentially the same. So with validity, we're talking about an argument as being valid or not. And an argument has premises and a conclusion. Now, instead of saying a certain argument is valid, we can also say that the collection of sentences, which are the premises of that argument, entail the conclusion, the sentence which is the conclusion. So we can say that a collection of sentences, here phi1 to phi n, entails a sentence phi, just in case every valuation that makes all of the sentences phi1 to phi n true also makes phi true. And hopefully it's clear how that's basically the exact same as the definition of validity, where, however, the difference is that with validity, we're talking about arguments, but we can just as easily think of an argument as a collection of sentences where you have a bunch of premises, here phi1 to phi n, and a conclusion phi. And you can wonder if that argument is valid, which is to say whether the sentences, which are the premises, whether they entail the conclusion. Now, the final thing about validity and entailment is that we can write the holding of validity using this fancy mathematical symbol, which is called the double turnstile. So when it is the case that sentences phi1 to phi n do entail phi, we can write them as related with this symbol here. So this formula here means that whenever all of phi1 to phi n are true, phi is true as well. And that is to say that if we constructed a truth table for all of these sentences, we would see that every row in which all of phi1 to phi n have true under their main connectives will also be a row in which phi has true under its main connective. And by constructing that truth table, we can test whether the sentences entail phi, which is also to test whether the argument with premises phi1 to phi n to the conclusion phi is valid. Now, once we understand the notion of entailment, it's a very short step to understanding the notion of equivalence. So we say that two sentences phi and psi are equivalent, just in case both phi entails psi and psi entails phi. So what it means for two sentences to be equivalent is for them to entail each other. So, and we'll see some examples of truth tables in a moment, as well as work through some examples. We'll construct them together, but before looking at those specific examples, what it meant for these sentences phi1 to phi n to entail sentence phi was for every row on which all of them phi1 to phi n are true is also a row in which phi is true. Now, therefore, when we think about two sentences being equivalent, just in case they entail each other, what that means is that if we construct a truth table for phi and psi, we'll see that they have, whenever phi has true under its, on a row, psi will also have true in that row. And whenever psi has true on a row, phi will also. So what that means is that when we're thinking about truth tables, for these two sentences to be equivalent is for them to have the exact same distribution of truth values under each of the rows for each of their main connectives. So here are some examples of equivalent sentences. So any two sentences of the following form are equivalent. First, not phi or psi, and not phi and not psi. So to say, and this is something that came up, I think, last week, to say that not phi or psi is true is the same as to say that not phi and not psi. So another way of putting this is that both of these are equivalent ways of formalizing the claim that neither phi nor psi is true. So for instance, if the claim is neither John nor Mary went to the party, you can formalize that as it is not the case that John went to the party or Mary went to the party. But you can also formalize neither John nor Mary went to the party as John didn't go to the party and Mary didn't go to the party. So that is to say that the sentences of these forms here, not phi or psi, as well as not phi and not psi, they are equivalent. And if you were to construct a truth table for both of these, you would see that they have the exact same distribution of truth or falsity under, on the one hand, the negation of the first sentence. So this negation here is the main connective of this sentence. And in the second sentence, the conjunction is the main connective. And if you were to construct the truth tables, you would see that the exact same distribution of truth or falsity holds beneath this connective and beneath this connective. Now, another example of equivalent sentences is that any two sentences of the form not phi and psi and not phi or not psi are equivalent. So again, if you were to construct these truth tables, you would see that they have the exact same distribution of truth values under their main connective. Now, these two facts about equivalences are called De Morgan's laws. So here are three more important semantic concepts. So where equivalence and validity hold between collections of sentences, these three additional semantic concepts are only hold for a single sentence. So if you're given a single sentence of the logic, you can ask whether that individual sentence is a logical truth, a logical falsehood, or a contingency. So another way of putting this, and this other terminology, which we might use more often, is you can ask whether the sentence is a tautology, a contradiction, or a contingent sentence. So beginning with the first, for a sentence phi to be a logical truth or a tautology is for every valuation to make phi true. And what that means in terms of truth tables is that for a sentence phi to be a tautology is for every row of the truth table, phi has true under its main connective. So in every possible assignment of truth values to the atomic sentences occurring in phi, phi overall gets the value true. Now, a sentence phi is a logical falsehood or a contradiction, just in case every valuation makes phi false. And in terms of truth tables, what that means is that a sentence phi is a contradiction, just in case every row of the truth table makes phi false. And what that means is that every way of assigning truth values to the atomic sentences in phi is one which makes phi overall false. So phi has the letter F under its main connective on every row of its truth table. And that's how we know whether phi is a contradiction by using the method of truth tables. Now finally, a sentence phi is a contingency or a contingent statement, just in case there is at least one valuation that makes it true and at least one valuation that makes it false. So that is to say that a sentence phi is a contingency, just in case it's neither a contradiction nor a tautology. And the way we tell that is once we've made the truth table for phi, we look under its main connective, and if sometimes we see t's and other times we see f's, that means that we know that phi is contingent. We know that phi is neither a logical truth nor a logical falsehood. We know that it's possible for phi to be true and it's possible for phi to be false. So here is an example of how we can use truth tables to test whether a given sentence is a logical truth or falsehood or a contingency. So we are now considering the sentence P or Q. So P and Q are basic atomic sentences. P might symbolize it is raining, for instance, and Q might mean it is snowing. Okay, so again, these basic atomic sentence letters represent simple sentences. And here we have disjunctions of the two simple atomic sentence letters. We have the disjunction P or Q. And we want to know whether the claim P or Q is contingent or not. Or, sorry, we want to know whether the sentence P or Q is a tautology, a contradiction, or a contingency. And as it happens, P or Q is contingent. And we can show this by looking at its truth table. So here we have constructed the truth table. So on the left-hand side, we have a list of the atomic sentences which appear in P or Q. And those are just P and Q. And then what we do is we list out below these two atomic sentences all the possible ways or combinations of truth values that these might have. So for P and Q, we have 4 possible valuations. We have 4 possible ways of assigning truth values to them. So there's a case where they're both true at the beginning, there's a case where they're both false at the end, and there's a case in which they differ. There's 2 cases in which they differ. So then once we have each possible assignment, which we just construct by listing out all the possible combinations, we then look at, given each of these assignments, or each of these valuations, what is the truth value of the entire sentence? So on the valuation that both P and Q are true, the entire sentence is true. And again, we know this, as I stressed in the previous lecture, the way that we determine the truth value of more complex formulas is we apply the rules for the meaning of our connectives. So the way that disjunction works is that a disjunction is true just in case at least one of its disjuncts is true. So in the case where both P and Q are true, it's true. In the case where P is true and Q is false, it's also true because all we require is that one of the disjuncts is true. In the case in which Q is true and P is false, it's still true because one of the disjuncts, the other one this time, is true. But then in the case where both P and Q are false, the entire disjunction P or Q is false because neither of the disjuncts are true. So once we've constructed this entire truth table in the way that I've just walked us through, we can look at the row which corresponds to the truth of the entire sentence on each valuation, which is we look at the column under the main connective of the sentence we're interested in, and that column shows us the different truth values that the whole entire sentence can have under each valuation. And here we see that there are some valuations in which is true. So the first three are ones in which the entire sentence is true. And the final one, it is false. So we see that there are some valuations in which P or Q is true, and there are some in which P or Q is false, and that's just what it means for the sentence to be contingent. But now let's consider a different sentence. This is the disjunction P or not P. So for instance, this might be a translation of the sentence, it is either raining or it's not raining. And as we can see here, that is a tautology, it's a logical truth. No matter what, it's either raining or not raining. And the way we tell that a sentence like this is true as a matter of logic, it's a tautology, as we construct the truth table and then we look at the column under the main connective. So because there's only one atomic sentence in this sentence P or not P, there's only the atomic sentence P. The truth table is very simple, so there's only two possible valuations we have to consider. We consider the case in which P is true and the case in which P is false. And in that case, as we build up the overall truth value of the entire disjunction P or not P, we see that if P is true, then not P is false. And then when we compare the disjunct P and the disjunct not P in that case, we have to add that at least one disjunct is true, P, so the entire disjunction is true. Now, when we move to the row in which we assume P is false, here we have the P disjunct is false, but not P is true, because the meaning of negation says that not P is true just in case P is false. So we get that the second disjunct in this second row is true, so not P is true. And that means that at least one of the disjuncts is true. So we see that in every possible valuation, the entire sentence P or not P is true. And that's just what it means for that sentence to be a tautology. That is, for every possible valuation, the sentence is true. So the final notions are those of consistency, inconsistency, and contradictoriness. Sorry, that's a bit of a mouthful. And in the readings, there's different words for the first two. So we can talk about, instead of consistency, we can talk about joint satisfiability. And instead of inconsistency, we can talk about joint insatisfiability. So what do these three things mean? Well, when we looked at tautology, contradiction, and contingency, those were properties of a single sentence. We asked whether a single sentence was a logical truth, for instance. But now, these notions are more similar to equivalence and entailment in that they hold between multiple sentences. So we say that two sentences, phi and psi, are consistent, just in case there is some valuation under which both of them are true. So in terms of truth tables, what that means is that if we constructed a joint truth table for phi and psi, we would see that at least one of the rows was one in which, under the main connectives for both phi and psi, you had true. That is, it's possible there's some way of assigning truth values to the atomic sentences that make both phi and psi true. Now, what it means for two sentences, phi and psi, to be inconsistent is for there to be no valuation under which both of them are true. So if we construct the truth table for both phi and psi, side by side, we will see that there's no row under which you see a true under the main connective for both phi and psi. That is to say that two sentences phi and psi are inconsistent, just in case there's no possible way of making them both true. Now the final notion is that of contradictoriness. Two sentences phi and psi are contradictory just in case there is no valuation under which both phi and psi receive the same value. So what this means is that in order for two sentences to be contradictory, it's not just that they can never both be true, but also they can never both be false. So that means if you constructed the truth table of phi and psi and compared them, you would see that there is no row, there's no valuation under which phi and psi have the same truth value. So they're never both true and they're never both false. They always have different truth values on every row. So what I've presented so far sums up the precise versions of the semantic notions which we have been building up to. And for this week and next, we will conclude the topic of our deductive logic by developing the technique of creating truth tables to test whether these various semantic notions, so for instance, entailment, equivalence, tautology, logical falsehood, contingency, and then consistency, inconsistency, contradictoriness, whether these things hold. So we'll be developing the skill of being able to tell whether sentences of our formal language have these properties or relations. So I'm going to conclude this first part of this lecture by giving some general remarks about these notions. And then in the next video, the second part of this lecture, I will work through some example questions where we do precisely what I've been saying, which is that we create truth tables to test whether sentences have these notions which I've outlined in this video. So here are some final remarks. First, for any two basic atomic sentences, for instance, P or Q, they are consistent. That is, any two atomic sentence letters are consistent because any valuation allows us to assign whatever truth values we want to atomic sentences. So that means that if you take two atomic sentences, it's possible to assign them both true. Another remark is that sentences P on the one hand and Q and not Q on the other are actually inconsistent. Now this might seem weird because these two sentences, P on the one hand and Q and not Q on the other, don't seem to be related to each other. So how is it that they can be inconsistent or impossible to be both made true? Now the answer is that focusing on this second sentence here, Q and not Q, this second sentence is a contradiction. It's a logical falsehood. It's impossible to make this sentence true. So if we made the truth table for this sentence, under the conjunction here, which is the main connective, every row would be false. It's not possible to make Q and not Q true. Q and not Q, for instance, symbolizes the sentence, it is both snowing and it's not snowing. And we can know as a matter of logic that it's false, that it's both snowing and not snowing. So because the sentence Q and not Q is inconsistent, there is no row of its truth table on which it's true. Therefore, when we compare it with any other sentence, there will be no row on which they're both true. So let me repeat this. And I want you to recall the definition of inconsistency. So two sentences, phi and psi, are inconsistent, just in case there's no evaluation under which both phi and psi are true. There's no way of making both of them true. And what that means is that if one of these two sentences is never true in of itself, then it'll be inconsistent with any other sentence that you provide. So because Q and not Q can never be made true itself, it will be impossible for both it and some other sentence to be true. So that is why P and Q and not Q are inconsistent. And in fact, for any other sentence you swapped in for P here, it would be inconsistent with Q and not Q because Q and not Q can never be true. Okay, third remark. Sentences P and not P are contradictory. So a sentence is contradictory with its negation. It's never the case that P and not P have the same truth value, and that's because the meaning of negation. Whenever P is true, not P is false, and whenever P is false, not P is true. So if we constructed truth tables and compare the truth tables for these sentences, we would see that they never have the same truth value on any row. So it's not just that P and not P are inconsistent, but furthermore, P and not P are contradictory. They never have the same value. But what I have in parentheses here is related to the fourth remark. So P and not P are contradictory. So it's never the case that P and not P have the same truth value. And what that means is that it's also never the case that P and not P are both true. So again, what it means for two sentences to be inconsistent is for it to be impossible for them to both be true. And now contradictoriness says something stronger. It says that it's impossible for the two sentences to have the same value, which means that it's impossible for the sentences to be both true or both false. So what that means is that any sentences that are contradictory are also inconsistent. So for any two sentences, if it's impossible for them to have the same truth value, then it's impossible for them to both be true. However, there are inconsistent sentences that are not contradictory. So it's possible for there to be sentences which can't both be true, but which can both be false. And so, for instance, P and Q and not Q is an example of two sentences which taken together are inconsistent, but are not contradictory because there is some row of their joint truth table in which they're both false. Whereas when we consider P and not P, on every row, they will have different truth values. There'll be no row in which they're both true, and there'll also be no row on which they're both false. Now, the final thing to note is that, and this is done in the readings, we can generalize these definitions of consistency, inconsistency, and contradictoriness to be about more than two sentences. So in the definitions I've given you here, I'm just telling you when two sentences are consistent, for instance, which is when there's some way of making both of them true. But we could add a third one, and we could say that the three sentences are consistent just in case there's some way in some valuation which makes all three of them true. And similarly with 4 or 5, or an arbitrary number of sentences. And similarly, we can do a similar thing with inconsistency. And those general definitions are given in the readings. But for the purposes of this course, I think we'll just be focusing on, in our exercises, on comparing two sentences, but it's with these notions. But it's worth noting that we can talk about the consistency or inconsistency, for instance, of more than just pairs, but also any number of sentences. So that concludes the first video of this lecture. And in the next video, I will go through some practice exercises.